All right, welcome back. So when we left off, we were talking about finding a subgroup of A5 that has order 12. And up until this point, what we've done is we've been able to list the orders of all elements in A5. We know now that every element of A5 is going to have order 1, 2, 3, or 5. And the question in the stream is, well, what about A4 as a subgroup of A5? And so my claim is, yes, that would work. As long as you justify which. So which copy of A4 inside of A5 you're looking at. And then I also kind of want to think about, are there any other possibilities? Any other subgroups of A5 that have order 12 but are not isomorphic to A4? So I kind of want to talk about both of those things taken together. So let's start with the A4 question first. So let me move on to a blank screen here. And let's think about the ways in which A4 is a subgroup of A5. So how is A4 a subgroup? So to do this, let me write out, so we have on our previous slide a classification of all the cycle types of elements inside of A5. And there's a total of 60 of them. But A4, on the other hand, only has 12 elements, so I can list out all of those. So I've got the identity, which has the cycle type just 1 plus 1 plus 1 plus 1. We have the 2 plus 2 cycles, 1, 2, 3, 4. And 1, 3, 2, 4, and 1, 4, 2, 3. Let me try and make some space here. 1, 4, 2, 3. So we have the 2 plus 2 cycles. And then we have all the 3 cycles. 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 3, 4, 1, 4, 3, 2, 3, 4, 2, 4, 3. So these are all the even permutations of 4 symbols. And so the question is, if we're going from 4 symbols, let's suppose that my symbols are called A, B, C, and D. And my group A4 is acting upon that set of 4 things. Well, the group A5 is going to be acting on a group of 5 symbols, on a set of 5 symbols. So let's call those symbols something new. Let's call them P, Q, R, S, and T. And A5 is going to be acting as permutations, even permutations, on that set. And so the question that leaves us, if we want to realize A4 as a subgroup of A5, in other words, the permutations acting on this set as a subgroup, isomorphic to a subgroup, rather, of the permutations, even permutations acting on this set, then the question that we have to answer is which symbols here are being associated with which symbols over here on the right. Every permutation of 4 symbols can be made into a permutation on 5 symbols. I'm going to call this function over here, I'm going to call it phi. Maybe I'll write phi the other way. Here. I'm going to call this function phi. And so we know for sure if phi, let me write it this way, if phi is a homomorphism, so if I can write down a homomorphism from A4 to A5, then I know, based on what we know about isomorphisms, if it's a homomorphism, it's going to be an isomorphism onto its, if it's a 1-to-1 homomorphism, then it's going to be an isomorphism onto its image. And so, therefore, phi of A4 will be a subgroup of A5. And because of the 1-to-1 criterion here, that subgroup will be isomorphic to A4. So basically, I just need a one-to-one homomorphism that sends every even permutation of 4 symbols into the set of all even permutations of 5 symbols. And the key to it is this. So I don't want to make this into a bigger deal than it actually is. If I'm permuting 4 symbols on the one hand in my domain, and I'm potentially permuting up to 5 symbols in the codomain, I just have to decide which of the 5 symbols that we're permuting over here in this group, which 4 out of those we want to let this A4 group be sent to permutations of. So, for example, are the positions 1 through 4 in A4 going to be sent to the positions 1 through 4, respectively, inside of A5? That would be one way of making this correspondence, right? Position 1 becomes position 1, 3 goes to 3, 4 goes to 4, and so on. But then that leaves out position 5. And so elements in the image of A4 would have to leave all of position 5 fixed. And so what this would do is it would position A4 as a subgroup of A5, or rather A4 is isomorphic to a subgroup of A5 in the following way. A4 would be isomorphic via this phi function here to the set of all permutations in A5 that leave 5 fixed. In other words, that leave 5 in place. So they can act upon the symbols 1 through 4, but they're going to leave symbol number 5 in place. And that's one way. If we keep to the same cycle notation as we used here to list out all the elements of A4, all of these elements written in cycle notation can be thought of as elements in A5. We're just not writing 5 as part of any of these cycles. That means that 5 must be fixed under all of these permutations. This is probably what mathematicians would think of as the most natural way to realize A4 as a subgroup of A5, is just to declare that this 5th symbol is extra. And so none of the permutations in A5 are going to do any, in A4, in the image of A4 under this homomorphism, none of those are going to do anything to that 5th symbol. Okay, so all of that is to say that this is one way of identifying a subgroup of order 12 inside of the group A5. And we could get that, by the way, by just looking at these 3 cycle types, right? The 3 cycle types that we saw in the A4 example on the previous slide, but then taking only those elements, only those that fix the 5th symbol, only those that leave 5 alone. And that would realize a 12-element subgroup of A5. So what I want to talk about now is there another way to do this? Is there another subgroup of order 12 that we can locate inside of A5 that's not isomorphic to a copy of A4? In particular, I kind of want to think about the question, is there an abelian subgroup? Is there an abelian subgroup of A4? Having order 12. And so this is a provocative question, because we know for sure that in general permutations of any number of symbols more than 2, permutations generally don't commute one with another. And so the whole permutation group, S5, A5, those are not abelian groups. But that doesn't mean that they can't have subgroups within them that actually are isomorphic to abelian groups. I mean, a simple example would just be the cyclic subgroup generated by a single 2 + 2 cycle. So an example of a cyclic subgroup, an example of an abelian subgroup would be a cyclic subgroup. The subgroup, for example, generated by 1, 2, 3, 4. And since that element has order 2, that cyclic subgroup only has 2 elements in it. Right? The set of all powers of the 2 plus 2 cycle 1, 2, 3, 4 consists of itself, and then the identity, because its second power is just the trivial permutation. And so this is isomorphic to the cyclic group Z mod 2. And therefore is isomorphic to an abelian group. Even though all permutations in the universe don't commute with one another, all the permutations in this set certainly do. And we could do the same thing, for example, to find a subgroup isomorphic to Z mod 3, and therefore abelian, just by taking the cyclic subgroup generated by any 3 cycle, any element of order 3 inside of A4. So, all right, if we continue to build that up, can we get to a subgroup, not necessarily a cyclic subgroup, but an abelian subgroup of order 12? So here's where we're going to kind of reach into what we know from Chapter 8 about direct products of groups. So I want to reframe the question one more time as follows. What direct products of cyclic groups have order 12? Direct products of cyclic groups, because cyclic groups are abelian, direct products of cyclic groups will definitely be abelian groups. And so a good place to continue our search for order 12 subgroups of A4 would be to look at these direct products of cyclic groups. That's going to give us a lot of possible abelian groups to which this supposed abelian subgroup of order 12 is isomorphic. So the way to figure out what are the isomorphism classes of direct products of cyclic groups that have order 12 is just to think about the different ways in which 12 can be expressed as a product. So how do we factor the number 12? One way of factoring it is just to do 12 times 1. But after that, we can also do 6 times 2. And we can also do 4 times 3. But then since 6 can be factored into 3 times 2, and 4 can be factored into 2 times 2, we could also do 3 times 2 times 2. So here are 4 different ways to factor the integer 12 in a non-trivial way. And, non-trivial means we don't have any 1s hanging out here, because those aren't interesting. And each of those corresponds to a potential direct product of cyclic groups. On the one hand, the factorization of 12 as itself would correspond to just the cyclic group Z mod 12. The factorization as 6 and 2 would correspond to the direct product of Z6 with Z2. That would be a direct product of cyclic groups that has 12 elements, because the number of elements is going to be the order of this group multiplied by the order of that group. That's 6 times 2. Same thing with 4 and 3. That would then correspond to Z mod 4, direct product Z mod 3. And then 3, 2, and 2, that would be the direct product of the 3 groups Z3, Z2, Z2. Direct product, direct product. So if there's an abelian subgroup of order 12, it turns out, by the fundamental theorem of finite abelian groups, which we haven't gotten to until our last chapter, that it's going to have to be isomorphic to one of these 4 examples. But these 4 examples are not all distinct from one another. So let's sort of whittle down this list a little bit before we go any further. We actually did the same thing for direct products of cyclic groups of order 12 in one of our videos for this past week, but we'll do it again. So we know, for example, that Z4 direct product Z3 is going to be a cyclic group. And it's going to be a cyclic group because 4 and 3 are relatively prime. And therefore, because Z4 direct product Z3 is a cyclic group, and it has order 12, that must mean that it's isomorphic to the cyclic group of order 12, the prototype, the original, the OG Z mod 12. Okay. So that means that my first and third examples on my napkin here are actually not different examples. So I'm going to erase the second one. So Z4 direct product Z3 is the same up to isomorphism as Z12. So we don't need to list it separately. And for the same reason, Z3 direct product Z2, which we also saw in this week's videos, because 3 and 2 are relatively prime. That's isomorphic to Z mod 6. And therefore, these two examples, Z6 direct product Z2 and Z3 Z2 Z2, those two are isomorphic to one another because this factor is isomorphic to that factor, and the other factor is Z mod 2. So for the same reason, I'm going to remove this last entry from my list. So up to isomorphism, there are only two groups that we can make via direct product of cyclic groups that have order 12. Okay? We can either do Z mod 12, which is cyclic, or Z mod 6 direct product Z mod 2. So let's think about the orders of elements in those two abelian groups. Z mod 12, because it's a cyclic group, has got to have a generator. And that generator is tasked with generating the entirety of the group of 12 elements. And therefore, the generator for Z mod 12 has got to be an element whose order is 12. So the question in front of us then is, are there any elements of order 12 that we could use inside of A5 to generate a cyclic subgroup of order 12? And evidently, looking at our list, that answer is no. Every element of A5 is going to have either order 1, order 2, order 3, or order 5. I guess there's one. No, we decided there was no 3 plus 2 cycles, because that would be an odd permutation. So that's the best we can do. So there are no elements of order 12 in A5, and therefore we can rule out the possibility that A5 has a subgroup isomorphic to Z12. What about Z6 direct product Z2? Well, this Z6 factor is going to imply the existence of an element of order 6. Because in the group Z6 direct product Z2, a generator of Z6, comma, really anything in Z2, is going to give me an element in that group of order 6. But there are no elements of order 6 in A5. And therefore, it's not possible for any subgroup of A5 to be isomorphic to Z6 direct product Z2 either. So because there are no elements of order 12 or order 6 in A5, neither of these two is possible. And it turns out, again by the fundamental theorem that we're working towards this semester, that these two abelian groups, Z12 and Z6 direct product Z2, those two abelian groups are the only possible direct products, the only possible abelian groups of order 12 up to isomorphism. And so we have to conclude here that there is no abelian subgroup of A4, I guess I did mean A5. That's a typo. That has order 12. We've ruled out all of those possibilities. What we haven't done is we haven't figured out whether there might be a different, up to isomorphism, non-abelian group of order 12 that is isomorphic to a subgroup of A5. To know the answer to that for sure, we need to know what are all of the possible non-abelian groups of order 12. And that is a rather interesting question. It's a question that I don't think we're going to have time this semester to really get to, because the question for classification of all non-abelian groups is a much, much deeper question than it is even for finite abelian groups. So let me make a recommendation of a great website. It's called the Group Properties Wiki. This is developed by a grad student who studies abstract algebra, I want to say University of Chicago. But it's got just a wealth, everything you could ever want to know really about finite groups. He's made an effort to tabulate, and it's just stunning how deep this wiki goes. So if I want to find groups of order 12, so here's what I'm looking at. We can find this website at groupprops.subwiki.org. So this is what it looks like. It looks just like Wikipedia. It's just the Wikipedia for group theory, basically. And so I'm just going to do a quick search. Groups of order 12. Groups of order 12. So what this site has actually done is it's tabulated what are all of the groups of order 12 that are known, that are possible up to isomorphism. And so, according to this, there are 5 groups up to isomorphism that have order 12, and here's the list. Here's the cyclic group Z12 that we were talking about a moment ago. Here is the direct product of Z6 with Z2 that we also saw a moment ago. Here's A4, which was Colleen's insight that she put into the stream just a few minutes ago that says, hey, this is a great example of an order 12 subgroup of A5. But then there are these two other choices. A dihedral group of order 12, so that's the dihedral group of the hexagon, and also what's called a dicyclic group of order 12. So we haven't talked about dicyclic groups, but these are kind of nice examples that are kind of like dihedral groups, but they're put together in a slightly different way. So let's take a quick moment and just see if we can convince ourselves that, let's just use a dihedral group as an example, that the dihedral group of order 12, in other words, the dihedral group of the hexagon, is or is not a subgroup of order 12 inside of A5. So now the question is there a subgroup, let's call it H, isomorphic to D, I call it D6, the dihedral group of the hexagon, that is a subgroup of A5. So to answer this question, let's think again about what the elements of D6, the dihedral group of the hexagon, actually look like. What do we know about them? What do we know about their orders? So the dihedral group of the hexagon, D6, is going to be the set of all symmetries of a regular hexagon. And so we know the identity symmetry is an example. We know that we have rotation by 60 degrees counterclockwise, and that's an element of order 6. So r squared is in there, r cubed is in there, r to the 4th is in there, r to the 5th is in there, r to the 6th is the identity. And then we have the rotation about one of its designated axes of symmetry, and the product of that reflection with each of the rotations, tr, tr squared, tr to the 3rd, tr to the 4th, tr to the 5th. And we can classify, based on what we know about symmetries, we can classify the orders of each of these elements. Let me just sort of give away the classification here. The orders of these elements are going to be 1, 2, 3, and 6. Clearly, order 1 is going to apply only to the identity element. Order 2 is going to apply to each of the reflections, and it's also going to apply to the 180-degree rotation, r to the 3rd power. So there are my elements of order 2. My elements of order 3 are going to be the rotations by 120 and 240 degrees, respectively. And my elements of order 6, those are going to be my rotations by 60 and by negative 60, or 300 if you like, degrees. So there are the orders of the elements in the dihedral group of the hexagon. So it has elements of orders 1, 2, 3, and 6. And if this were isomorphic to a subgroup of A5, that must mean that there's a subgroup of A5 that has exactly one element of order 1, has exactly 1, 2, 3, 4, 5, 6, 7 elements of order 2, 2 elements of order 3, and 2 elements of order 6. And looking in my table of the orders of elements in A5, I might be able to sort of take some subset of elements that has the right number of elements of order 1, elements of order 2, elements of order 3. But I'm certainly not going to be able to get the requisite number of elements of order 6, because A5 has no elements of order 6. So we have to give this one a big no also, because D6 has elements of order 6, but there are no elements of order 6 in A5 at all. Now it's a different question of whether or not in A6 we might be able to do this, because in A6, well, I don't know. In A6, I think we'd be able to do it because we would have access to some different cycle types. But yet, I'm not sure that we could make a cycle type of an even permutation that gives me the order 6, even in A6. So maybe in some higher alternating groups, but certainly not in A5. There is no subgroup isomorphic to the dihedral group of the hexagon. And I won't go into the dicyclic example either. Just I don't want to get us off onto a tangent before the exam tomorrow. So I want to move on and sort of turn the page and do one more different kind of problem before we wrap up the stream today. Before I do that and move on to something else, are there any other questions about this example or any things you want to, in particular, see us address before we move on to do one more question before wrapping up? Post those in the stream in the next minute or so. I'm going to be getting the next example together while you do that. So to wrap up, I think what I'd like to do is just quickly go over, well, let me say it this way. Let's suppose that we wanted to find, I'm going to say it this way. Let me just write out what I'm thinking. What I'd like to know is, what is the automorphism group of Z30, how about 48 as a direct product of cyclic groups? So I've just kind of put a scary thing on the screen. The automorphism group of Z mod 48. So I want to first think about what the automorphism group is. It's the set of all isomorphisms. So it's a set of functions from Z48 to itself. So what I'd like to know is, first of all, what is the set? So how many elements does this set have? And then second of all, what can I say about its isomorphism class as a direct product of cyclic groups? So first of all, let's think about Z48 as a cyclic group. If we think about it as being one of these clock-like groups, it's just that my clock has 48 numbers around its face instead of 12. 0, 1, 2, 3, 4, and so forth. And then 24 would be at the bottom of the clock, 25, and so forth, 46, and 47. So my clock would look something like this. Now, if I have an isomorphism from this group to itself, because these groups are cyclic, we know that an isomorphism of cyclic groups, this is a key fact, an isomorphism of a cyclic group must send a generator to generator. So if my question is how many different of such isomorphisms exist, really, my isomorphism is going to be completely determined by where a generator goes. And that's probably the most important thing to know about isomorphisms of cyclic groups, is that once we specify where a generator goes, we know the entirety of phi. We know everything that it does. This is similar to in linear algebra. If you tell me what a linear transformation of vector spaces does to a basis of its domain, then because the entirety of the algebra in that vector space is dependent on that basis, we then know what that linear transformation does to the entire vector space. Same deal here with generators in relation to the whole group. So, okay. The question I would then ask is, let's single out a generator in the domain. Let's use the most obvious one, the number 1. So if you tell me what phi of 1 is, If you tell me what phi of 1 is, then you've told me the entire isomorphism, because 1 generates the whole group. So then what are our choices? How many different places can we send the number 1 to? Well, here's where we need to plug in a fact that we knew from Chapter 4. And that is, how many generators of Z48 are there? Well, to be a generator of Z mod 48, it has to, an element would have to have order 48. How many elements of order 48? And that's a question that's answered by the Euler-Toshin function, phi of 48. So if we want to figure out how many generators are possible, we'll compute phi of 48, which I would have to do by finding the prime factorization of 48 into prime powers, at least. 48 is going to be 6 times 8. That's going to be 16 times 3. So that's the way I want to think about it. 2 to the 4th times 5, 3. And then, because 16 and 3 are relatively prime, we can split it apart, right? It's multiplicative over relatively prime integers. And the Euler phi function of 2 to the 4th is 2 to the 4 minus 1 times 2 minus 1. So that's the prime power formula. And then phi of 3 is going to be 3 minus 1, because 3 is prime. So if I multiply this out, 2 to the power 4 minus 1, that's 2 cubed, that's 8. Multiplied by 2 minus 1, multiplied by 3 minus 1, I get 16. So the first thing that I learn here is that there are 16 possible generators. There are 16 places where I could send the generator 1. So 1's an example of a generator, and so is its inverse 47. 2, 3, and 4 would not be examples of generators, but 5 would be. I put that in my list also. 5 is a generator. And its inverse in Z48 would be 43. That's also a generator. And so on and so on. So there's 16 generators that we could select here. And therefore, each one of those different choices of where to send my generator, 1, is going to give me a different automorphism of Z48. So we know for sure that the automorphism group of Z48 is going to be a group that has 16 elements. Which group of 16 elements is it isomorphic to? Here's a theorem that we can take to the bank that's actually isomorphic to U48. So to actually justify this, we would have needed a theorem, which if you're following along in Gallien's textbook, this is theorem 6.5 in the chapter on isomorphisms. So this just means that there's 16 different ways of making an isomorphism from Z48 to itself. And those different isomorphisms compose together in the same way that the multiplicative units mod 48 do, which is not especially challenging to convince yourself of, because if I compose these two together, what I'm going to end up doing is sending the element 1 to the product of where the first thing sends, where the first automorphism sends 1, and the product of that with where it sends, where the other automorphism sends it. And so they're going to compose together in the same way that these relatively prime integers to 48 multiply together. And that is exactly the algebraic structure of U48. Okay, so that gets us halfway there. How do we get the rest of the way through? Which is to figure out what is this isomorphic to as a direct product of cyclic groups. So what is U48 isomorphic to as a direct product of cyclic groups? Well, to figure that out, we end up using the same process that we used to discover the Euler phi function of 48. Right? We factored 48 into the prime powers, 2 to the 4th times 3. And then use the fact that for the same reason that the Euler phi function is multiplicative across relatively prime products, so too is this U group multiplicative across relatively prime direct product. So it's u of 2 to the 4th plus u to the 3rd. Again, because 2 to the 4th and 3 are relatively prime. And that's a theorem. If you're following along in Gallien's textbook, let me get the citation for you on that one. That is theorem 8.3. But then we know how to simplify each one of these U groups as a direct product of cyclic groups. So this U3, because 3 is a prime power, U3 is a cyclic group, prime power of an odd prime, and therefore it's a cyclic group, and so its order, it's a cyclic group of order equal to phi of 3. And since 3 is prime, phi of 3 is 2. So that just gives me a z mod 2 in that factor. Meanwhile, u of 2 to the 4th, because it's a power of 2, is not cyclic in and of itself. It, on the other hand, is isomorphic to z of 2 to the 4 minus 2, direct sum z2. And so what do I get here? z4, direct sum z2, and z2. And that completes the problem. So if I want to understand the algebraic structure of the automorphism group of Z48, the first thing I would do is realize that this group is isomorphic to U48. And then we know how to decompose any U group into a direct product of Z groups, just by first finding its prime factorization and then splitting a direct product across that prime factorization of U groups, and then transferring those U groups to Z groups using this last theorem that we had. So this again is probably a deeper example than the kinds of problems I'm going to ask you on the exam tomorrow, but it gave us the opportunity to revisit questions about isomorphisms. They send generators to generators for cyclic groups, and then also questions about how to reduce a U group into a direct product of Z groups. So I hope this was helpful today. I'm going to put these videos up into the YouTube channel, and feel free to continue the conversation via Slack if you have questions about anything we did here today, or you can drop questions and comments in the Twitch archive or on the YouTube video that goes up on this. And I will see you for the exam tomorrow.